In this video, I'm going to use this Numberphile video on the Langlands program featuring Edward Frenkel as sort of an excuse to sort of play around with Wolfram-Cloud Mathematica. So I'm not going to explain anything because I don't understand it really, but there's this correspondence between two things, and I'm going to sort of generate a series in Mathematica, sort of both sides, and sort of show they're the same, but mainly just an excuse to play with Mathematica. Okay. So eventually, ultimately, there's some sort of sum or series over primes, but I'm just sort of starting out here with a prime, so 5. So just p equals 5, and then later on we'll turn that into some series over primes. And then we have this equation. Well, it doesn't look like an equation here, but y squared plus y equal x cubed minus x squared. And we're looking for solutions, and we're going to be, in particular, looking for solutions where x and y are integers, and we're going to be working with a modulus of the prime. So our x's are only allowed to go, our modulo the p, the prime, the y's, and then these combinations are also modulo prime. We'll get there. Okay. But so for now, because the x and the y are that we're interested in only are modulo the prime, then I'm going to only go up to the prime. So I have a for loop in Mathematica here, and a for loop in Mathematica is a method with 4 arguments. So let's look first at this inner. So the first argument is the initialization. The second argument is the condition under which to continue. The third is the increment. And then the fourth argument is what you want to do in the iteration. And so I'm just printing out something. I'm printing out what my x was, what my y was, what the left-hand side was, and what the right-hand side was. And then I have nested loops. So the fourth argument of my outer loop is my inner loop. And if I wanted to do more than one thing in the loop, then if I have like multiple, I'll say statements, that I want to perform inside in that fourth argument, the things I actually want to execute. If I want to do more than one thing, then I separate them by semicolons, which we will see. Okay, so that's the syntax of for loops. And enter that, and then we see just going through my combinations of x and y and figuring out the left and right hand side. And I haven't I've done the modulus on the x and the y, but I haven't done the modulus on those quantities, on the y squared plus y, or the x cubed minus x. So that's what will come next. So Mathematica has a mod method, and so I am taking the mod of these things with respect to p the prime. So that's just, that mod is just this one modification to what I had above. And now, so this, the prime was 5. So I'm taking this 48 at the end, this 20, and that will be 0 when I mod the 5, and this 48 will be 3. There it is, 0 and 3. Okay. So now I only want them when it's a solution, with all this modulus stuff going on, when it's a solution, when the left and the right-hand side are equal. Okay, so here's my outer for loop on X, my inner for loop on Y. I'm having multiple things I'm doing, so separated by semicolons. So I am calculating the left-hand side. I'm calculating the right-hand side, and then I'm bringing in an if. So an if is, again, a method in Mathematica, and there are sort of three parts: the condition, the question, the true-false question, and what you want to do if it's true and what you want to do if it's false. Now, here is the beginning and the end of the print, and then this if here. So that's the print. So this is the end of the print. Here is the first argument of the if left is equal to right with two equals, equal, if left equal right. I'm printing. I have my third argument of the if is just a blank. I don't care to do anything if it's not true. Here's the end of my if. Here's the end of my for loop of the inner for loop and of Y, the outer for loop of X. And so now I'm still printing, and so I'm printing when the left hand and the right hand sides are equal. And in this case, that happens to be when they're both zero, but that didn't have to be. That was just what happened to be in this case with P of 5. Okay. Now, what we want to do is we're not so much interested in the solutions as the count of the solutions. Again, I have no idea why, but I'm just playing around with Mathematica. All right. So I introduced a counter. I wanted to do this all sort of in one line in Mathematica. So you sort of turn one line into multiple lines, as we already said, with semicolons. So I'm initializing a counter. The word count is reserved. So I called it sol count for like solution count. Initialized it to 0. There's my outer loop. There's my inner loop. This is my execution stuff. Within the inner loop, determine the left side, the right side, ask if they're equal, increment my sol count. Then when I'm all done, just print out the number of solutions, which we saw above. There were 4. Okay, so now I'm finding the solutions, counting the solutions. So now, and that was all for P of 5. So now I want to do it for other primes. And so I'm going to introduce another loop, and I'm going to, and another if. So I'm going to, this is ultimately, right now, this is just its own little loop, but this is going to be sort of an outer loop that's going to contain all that was above. So I'm saying I'm starting with P equals 2 and going up to 50 and incrementing by ones. And then here's my if. If has 3 things: a question, what you want to do if it's true, what you want to do if it's false. And there is a built-in method in Wolfram-Cloud Mathematica called PrimeQ. So is the argument a prime? And so that loop there gave me the primes: 2, 3, 5, 7, 11, 13, yada, yada. Okay, so now I'm going to put these pieces together. I'm looping over the p's. I'm asking if p is a prime. If p is a prime, I'm setting my solution counter to 0. I'm doing my loop over the x's, over the y's. I'm calculating the left-hand side and the right-hand side. With the moduluses, I'm asking if the left is equal to the right. I am incrementing my solution counter, and I'm printing out the solution counter. I'm printing that out, and so I'm just showing here the number of solutions for, I'm going to improve on this, but this was for p equals 2, for p equals 3, for p equals 5, for 7. And this is this parenthesis, I lost it. This parenthesis asterisk and then asterisk parenthesis is a comment in Mathematica. So I can put some in, because these are getting fairly long. It's probably a good idea to put some comments in there. Okay. So here are the solutions for the different p's, only for the p's in our prime, and I decided to go up to 50. All right. Now I want this collection of what he was calling AP. It was the prime number minus the number of solutions. So he's collecting for the primes. There is this quantity A of P. And so that's what I'm doing next. I'm going to make a list in Mathematica of the primes. So he had that table. So I am making sort of a list like this. So, and I called it APS, the APs, whatever. So he had A of P, I called it AP, and then there were more than one of them, so I called it APS. Okay, so I'm starting off just with an empty list. Here's my loop over P's. I'm going up to 200. I'm asking if it's prime. If it's prime, I'm going to play my game and count solutions. So I set my solution counter to 0. I have my loop over X, my loop over Y. I calculate my left-hand side and my right-hand side. I say if they're equal, I increment my solution counter. And then when I'm done the X and Y loop, then I'm going to make a pair or a tuple, which is going to be the prime in this AP. So I called it my tuple, which is going to be just a simple, I have that list I'm making is actually going to be a sort of a list of lists. So here's my little list, my tuple. It's just brand spanking new. And then I added the P, the prime, and I added this AP, which was the prime minus the solution count, the prime minus the solution count. And then once I had the tuple, then I added it to my list of tuples, which is a list of list. Okay, so here we go. And Mathematica spits it out pretty quickly. And then one thing they talked in the video was the number could be positive or negative. So here's a plot of it. It can grow with the prime, and there's some talk about square root. So I just wanted to plot that. And then I was looking, so you could sort of see this, I don't know, growing some, I'll call it the envelope of the function, maybe growing, not linearly. I think they were saying it was square root. First, I plotted it with, you'll see below, a plot with a square root, and it wasn't what I would say an envelope, that it was that there were points outside of it. So then I just sort of put other numbers in there to sort of get it on the outside. And I don't know what the precise number is, or if there is a precise number or anything like that, but just playing around, I came up with like, I don't know, square root of 3, or the whole thing square root of 3x. And this is just, playing around. I didn't go very high. I only went to 200, but just sort of playing around. So, and then put the two sort of together, and we sort of see they're within there. I could do it like a negative square root on the other side and get sort of the other side of the envelope, if you will. But okay. And then this whole game, this Langlands program, is about connecting things. And so then we sort of have this jump to this other thing. Talked about harmonics and generating functions. And then all of a sudden he has this product. So it was, let's see if I can scroll enough in the video to come up with this. Here's this product. Q1 minus q squared, 1 minus q to the 11. No idea where this 11 pops up. But 1 minus q squared, 1 minus q squared, 1 minus q cubed squared, and then there are these 11s, 1 minus q to the 11th squared, 1 minus q to the 22 squared, 1 minus q to the 33 squared. I can only imagine that somehow this 11 is somehow characteristic of our, initial of this equation. I have no knowledge of that. I'm just playing with Mathematica. Okay, but here's this product again. I'm just playing with Mathematica and seeing what it can do. And so I called it h of q, and it was q times then a product. And I have 1 minus q to the I. I'm taking my counter I going from 1 to infinity. So this is the 1 minus q raised to the I. And then that was squared. So that's the 1 minus q squared, the 1 minus q to the 1 squared, 1 minus q to the 2 squared, 1 minus q to the 3 squared. And then another term, 1 minus q raised to the parentheses I times 11. And that was also then squared. So that was the 1 minus q to the 11, 1 minus q to the 22, 1 minus q to the 33. So there it is. Enter that definition thing. Okay, I called it HQ. I just picked up an H because he was talking about harmonics. In Wolfram-Cloud Mathematica, you can do a series. So up above, I was going up to 200 in my prime. So I decided to do this expansion around this product up to the same number, 200. I probably should have made that a variable, but alas, you can do better than me. And so we're doing this expansion. And you can see I'm not really pressing Mathematica Wolfram-Cloud very hard. It's, spitting these things out relatively quickly. So here is this expansion. And then the idea here is that for the prime powers in this expansion, the prime powers, the coefficient is matching that AP. So where was our 5? So our 5 that we played around with a bit had, the prime was 5, the number of solutions was 4, so the prime minus the number of solutions was 1, and there that coefficient was 1. In fact, there were 4 solutions for 2, for 3, and for 5. But again, this coefficient here is this AP, this prime minus the number of solutions. So for 2, it was 2 minus 4, minus 2. And for the 3, it was 3 minus 4, minus 1. And then over here for the 5, it was 5 minus 4, the plus 1. So this generating function harmonic thingy with the 11th powers floating around seems to somehow be related to this counting problem of the solutions. Okay. Now let's make Mathematica work harder. You can extract out, Mathematica has a thing called the series coefficient. And so I can pull out a specific power, specific coefficient for a particular power. So I can do the series coefficient of my expansion. Can't work here directly with HQ. It wasn't working for me. But after I expand, then I can ask for Q expanded around 0, what is the coefficient of the 17th power? So I'm getting -2. And I didn't pick 17 for any particular reason, but there it is, -2. What do we want to go for? 23. Let's go for 113. I don't know. 113 was a 9. So we're picking out the coefficient. Okay. So now I'm going to get my APs again, my list of AP tuples again, but in this other way. So I have my loop over P's. I'm only interested in the P primes. I'm going to make a tuple. My tuple is going to be the P, the prime, and then this coefficient. So here's my expanded harmonic thing. And I'm taking the P coefficient of Q around 0. And then I'm going to add that tuple to my APS. And there is the result. And that result, let's see if I can down here say APS. I want to do APS. Shift Enter. So this was APS 2 above. Out 16 was APS 2. This is APS. But we can see there is this correspondence. So that's what this Langlands thing is presumably about. These correspondences. So we have this product, we have this solutions to elliptic equations playing in this modulo space, modulo over prime, and we're getting the same things. And then he started talking about symmetries and really lost me. So anyway, that's what I wanted to show you, just some excuse to play with Mathematica, and it made us play with for loops and modulo and ifs and what else? PrimeQ and products and all sorts of fun things. So that's it. Thanks for your attention.